Hey everyone, and welcome right into the explainer. I am so incredibly thrilled you're joining me today because we are going on an absolutely epic cosmic journey. We're going to start by looking at the largest scales of the universe, literally its very dawn. And then we're going to funnel all the way down into the microscopic quantum mechanics of black holes. And ultimately, we're arriving at the birth of some incredibly unexpected alien worlds.
So, think about this for a second. What in the universe actually connects the explosive birth of the cosmos, a massive scaffolding of completely invisible matter, and fiery planets orbiting supermassive black holes? I know, it sounds straight out of a sci-fi movie, but as we're about to see, these concepts are deeply interconnected threads that weave the entire fabric of our reality together. Here's our quick flight plan for today. We'll start with part 1, the dawn of the cosmos. Then move to 2, the invisible dark universe. After that, 3, mechanics of black holes. Next up is 4, seeking habitable alien worlds. And finally 5, black hole planetary nurseries.
All right, let's start right at the very beginning. Section 1, the dawn of the cosmos, setting the cosmic stage.
Okay, so this timeline breaks down the unimaginably rapid expansion of the early universe at roughly 10 to the negative 37 seconds after the Big Bang, which is an insanely small fraction of a second. The universe underwent cosmic inflation. It just grew exponentially. And the really crucial takeaway here is that microscopic quantum fluctuations, literally the tiny jittering of subatomic particles dictated by Heisenberg's uncertainty principle, were essentially frozen in place by this rapid inflation. It's like they were caught on camera. These microscopic jitters became amplified into the massive seeds that would eventually form entire galaxies. Fast forward to 380,000 years later, the universe finally cooled down enough for electrons and nuclei to combine. This made the previously opaque, glowing fog of the universe transparent, releasing the cosmic microwave background radiation that we can still detect out there today.
Moving right along, Section 2, the invisible dark universe, the scaffolding and accelerator.
Well, how did those early quantum seeds actually grow into the massive galaxies and structures we see around us today? The truly astounding part here is the sheer, mind-blowing imbalance of our reality. Everything we can see, touch, and observe with traditional light, every star, planet, dust cloud, you, me, everything, makes up just 5% of the cosmos. That's it. A full 95% of the universe is composed of stuff we cannot directly see. You've got 27% dark matter and 68% dark energy. We are literally the cosmic minority. To break down what these unseen forces are actually doing behind the scenes, dark matter acts as the gravitational glue of the universe. We know it has to be there because of observations like galaxy rotation curves. Vera Rubin famously studied these, showing that stars at the outer edges of galaxies are moving way too fast to be held in by just the visible matter. So dark matter provided this invisible gravitational scaffolding for the early universe to clump together. Dark energy, on the other hand, is doing the exact opposite. First confirmed by observing distant Type 1a supernovae, dark energy is this mysterious, repulsive force that's driving the accelerated expansion of the universe. It's actively pushing the whole cosmos apart. So in the midst of this expanding universe, sometimes matter just completely collapses in on itself. Section 3, mechanics of black holes, the gravitational titans. Let's establish exactly what a black hole is, mechanically speaking. The defining feature is the event horizon. You can think of it as the ultimate boundary of no return, where gravity is so incredibly intense that the escape velocity actually exceeds the speed of light. Nothing, not even light itself, can escape once it crosses that threshold. To make this a bit more tangible, just consider Sagittarius A star, the supermassive black hole sitting right at the center of our own Milky Way. The Event Horizon Telescope actually captured an image of this monster, confirming it has a mass of about 4 million times that of our Sun. 4 million! And all of that is packed into a mathematically dense singularity. And honestly, this brilliantly illustrates one of the greatest tensions in modern physics right now, the information paradox. Under classical general relativity, a black hole is basically characterized by only 3 things: mass, spin, and charge. Any other information about whatever fell into it, it's permanently lost. But in 1974, Stephen Hawking applied quantum mechanics to the event horizon. He discovered that vacuum fluctuations near the boundary actually lead to particle creation. This means black holes emit thermal radiation, what we now call Hawking radiation, and they slowly evaporate over time. But hold on. If a black hole evaporates away completely, what happens to the complex quantum information of the stuff that fell in? Does a pure, organized quantum state just turn into a mixed, chaotic state? Actually, this paradox is still intensely, and I mean intensely, debated by physicists today. So, with all these dark voids and destructive black holes, where can complex life actually survive? Section 4. Seeking habitable alien worlds. Oases in the dark. Traditionally, our search for life is super focused. Using data from things like the Habitable Worlds catalog, we usually search for rocky planets sitting comfortably in the Goldilocks zone. Not too hot, not too cold, just right for liquid surface water to exist. We're looking at planets like Kepler 186f, orbiting a red dwarf star, or Kepler 452b, which orbits a G-type star that's actually very similar to our own sun. The standard textbook model of planetary formation dictates that planets are born in the gentle, rotating, protoplanetary disks of dust and gas that surround infant stars. That's the normal way it happens. But what if stars aren't the only places planets can be born? Section 5. Black hole planetary nurseries. The cosmic surprise. I absolutely love this quote from researcher Bhupendra Mishra. He said, "We were astonished." And let me tell you, when the scientific community is openly astonished, you know it's good. They discovered that the incredibly chaotic, turbulent environments around active supermassive black holes, which are actively eating material and often outshining entire galaxies, might actually be the birthplaces of millions of planets. Okay, so the crucial point here is the actual mechanics of how this wild idea works. Supermassive black holes are surrounded by these massive, swirling disks of gas and dust called active galactic nuclei, or AGN accretion disks. While the inner parts are fiercely hot and completely destructive, the distant edges of these disks, tens of parsecs away from the center, actually mimic the cool protoplanetary disks of regular infant stars. Through a mechanism known as streaming instability, the immense amount of gas and dust in that disk clumps together into massive filaments. And because a black hole's disk has so much more material than a standard star's, it doesn't just make a few rocky planets. It could birth millions of Jupiter-mass planets. The researchers actually describe them as giant lava balls. And once they form, these planets are gravitationally stable, eventually migrating outward, safely away from the black hole. Which brings us to our final thought for today. If millions of massive planets can literally assemble themselves in the incredibly violent, fiery accretion disks of supermassive black holes, where else in this dark, invisible universe might unexpected oases be hiding? We've gone all the way from the microscopic quantum seeds of the Big Bang to giant planets orbiting black holes, proving that the cosmos is just far more creative than we ever could have imagined. Keep wondering, keep exploring, and hey, thank you so much for joining me for this explainer.